Section 2.6, Graphical Integration in Motion Analysis. This is a fairly short section. It highlights how you can do integration visually, which you may have some experience with already at this point. And it's summed up with these two graphs shown on the learning objectives slide. So the learning objectives slide tells you exactly what you want to take away from this. That if you have a graph of acceleration versus time, then if you take the area under the curve over some time interval, that will give you the change in velocity. Pretty cool. Similarly, if you have a graph of velocity on the vertical scale versus time on the horizontal, then the area under the curve will give you the change in position. All right, let's take a closer look at what's going on here. So integrating acceleration. Given a graph of an object's acceleration versus time, we can integrate to find velocity. Our fundamental theorem of calculus gives the following, right? That the change in velocity, v1 minus vo, or v naught, is equal to the integral from some initial time to some later time of the acceleration dt. We did this integral previously when we were deriving our super equations, but when we were deriving those equations, we only derived them in the case that the acceleration was constant with respect to time. And that allowed us to pull the acceleration outside of this integral. In this case, acceleration might be changing with time. And that means that this integral might not be so simple. We could find an equation for how acceleration depends on time. Or if we have a graph of how acceleration varies versus time, then we can just find the area under the curve between that acceleration curve and the time axis. And that will allow us to calculate this definite integral on the right side. And that would then give us the change in velocity that is on the left side. So this is a pretty nifty, quick technique. It's very visually based, that as long as your graph is properly scaled, we can go back to the graph on the previous one. As long as this graph has proper scale of how much acceleration there is, what definite time intervals, you can get concrete numbers for the change in velocity there. Now, the other one we're going to take a look at is how the velocity in time versus time graph can give us the change in position. So if we integrate the velocity instead of integrating the acceleration, then when we integrate that, we get the change in position. So delta x is equal to the integral of the velocity dt. Once again, if we know the acceleration is constant, and we know how the velocity depends on the acceleration, we could put in an equation there, do the actual integral. But if it's something more complicated and we don't have an explicit equation for how the velocity depends on time, then we can use a graph and note that the area between that velocity curve on the graph and the time axis is going to give us this integral, which is just the change in position. So let's look at an example of this to make it a little less abstract. This is a pretty cool graph of data, actually. This is acceleration versus time for a person's head and torso in a whiplash incident. So it could be on a roller coaster or in a car accident, some sort of whiplash incident. And we notice that the torso starts accelerating much sooner and more gradually, and then the head has a larger acceleration that's delayed onset, and so it's much more dramatic. It's more of a jerk, actually. It's a quicker rate of change of acceleration with respect to time. That's an aside, though. You don't need to learn about jerks in this class. We keep it nice. Right, so anyways, if we want to find out how fast the torso is going as it undergoes this acceleration, at 0.11 seconds, assuming that it's initially at rest, then we can find the area under the pink curve. So it's really just this black curve that's been drawn down here, right, where this is 110 milliseconds. That's what's shown on the graph here. These are plotting milliseconds. So it's going up to this line. And so if we just find the area under the curve, that will give us the change in velocity. If the initial velocity is 0, that will give us the final velocity. So we notice that with the pink curve, they've conveniently divided it into 3 areas that are much easier to calculate. First, there's area A, which is right on the time axis. So that's an area of 0. Cool. That's really easy to calculate. Then we have B, which notice what shape is B? B is a triangle. So we can find the area of a triangle with half the base times the height. So that's what they did here. 1/2 the base is 60 milliseconds or 0.06 seconds times the height, which is 50 meters per second squared. Cool, so that gives us that area. And notice when we multiply the seconds times the meters per second squared, that gives us units of meters per second. So that's already suggesting that we are getting a velocity out. Excellent, that's a good check. Finally, we have this small rectangular area C, which we can just use length times width. So the width is 10 milliseconds times the length is 50 meters per second squared. So we get 0.5 meters per second. So the total area under the curve is 2.0 meters per second, and that tells you how fast the torso is going before the head even starts to move. So, neat example, you could figure out how fast the head is moving after another few milliseconds, but this illustrates the idea of doing a graphical integration as opposed to following the full normal integration rules. So, that brings us through this section.